The Philippine Sea does not announce itself. There are no landmarks, no coastal lights, no reference points beyond the horizon. Just open ocean in every direction, 2,000 meters of water beneath the keel, and the complete absence of anything that is not the ship and the sea. At 2:09 in the morning, the surface is running a 2-meter swell from the northwest. Long and regular, the kind of sea state that experienced sailors call benign, and that makes working below decks feel like operating inside a slow pendulum. The sky is overcast, no moon, no stars. USS Curtis Wilbur makes 24 knots on a northwesterly heading. Her wake a phosphorescent trail that glows briefly in the darkness before the ocean closes over it. She is 340 nautical miles southeast of the Miyako Strait. The nearest friendly port is Okinawa. The nearest unfriendly submarine is 14 nautical miles to the northeast, running at periscope depth at 4 knots on a closing intercept geometry. The crew does not know the submarine is there. The Type 039B has been tracking the Wilbur for 6 hours. Its passive sonar suite has been reading the destroyer's acoustic signature since the ship transited the outer boundary of the patrol zone at 2,000 hours. The 039B's commanding officer has been patient in the way that submarine operations require patience. Absolute silence, minimal helm corrections, a geometry of pursuit that uses the Wilbur's own noise to mask the submarine's approach. He has waited for the targeting solution to reach the threshold confidence level his doctrine requires. At 2:06 a.m., the solution reaches 94%. The doctrine requires 85. He does not fire immediately. He waits 3 more minutes. At 2:09 a.m., he gives the order. The U-6 heavyweight torpedo leaves its tube at a depth of 18 meters. It is a wake-homing system. It does not need an active sonar ping that would reveal the firing platform. The torpedo finds the Wilbur's propeller wake and follows it toward the hull. The time of run at 50 knots is approximately 41 seconds. In those 41 seconds, the Wilbur's passive sonar operator, who has been running an environmental noise assessment, hears something that does not belong to the ambient ocean. The tone is wrong. The frequency is wrong. He classifies it in 6 seconds. Inbound torpedo, close range, bearing 035. He keys the intercom. Torpedo, 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 inbound, bearing 035, close aboard. The officer of the deck orders hard rudder and maximum speed simultaneously. The conning petty officer repeats the order. The helm responds. The Wilbur's bow begins to swing to starboard. The countermeasure launcher fires 2 Nixie decoys and an acoustic jammer into the wake. The helmsman pushes the engine order telegraph to all ahead flank. The ship has 7 seconds. The U-6's wake-homing algorithm detects the course change in the Wilbur's propeller wash and compensates. The decoys degrade the acoustic lock partially. The torpedo loses the wake for 1.4 seconds, then reacquires it on the updated bearing. The hard turn has moved the hull laterally, and the torpedo's closing geometry has been altered by the course change. Instead of detonating directly beneath the keel at the engineered optimal standoff of 0 meters, the ordnance passes 80 meters beneath the hull at a lateral offset of roughly 60 meters and detonates at the end of its active pursuit run. The detonation of a 400-kilogram warhead at 60 meters lateral range and 80 meters depth does not breach the hull of an Arleigh Burke-class destroyer. The designers did not plan for this specific geometry, but the ship's structural margins absorb the kinetic loading. What the detonation does, what it is, in effect, designed to do even in a partial miss scenario, is transmit a pressure wave through the water column that strikes the hull across its full length simultaneously. Not a point load, a distributed impulse. The entire ship is accelerated laterally by approximately 3 feet in 0.8 seconds. Every unsecured object on the ship becomes a projectile. The Wilbur's hull rings like a struck bell. The noise is not a bang. It is a deep, sustained resonance that takes 4 seconds to decay, felt through every surface at once. transmitted through the deck plates into the soles of boots, through the bulkheads into palms pressed against them, through the frames into the teeth of every sailor aboard. The 3 gas turbine generators trip simultaneously, all 3. GTG number 1 trips on its vibration sensor. GTG number 2 trips when the shock pulse causes a momentary voltage spike on its output bus that the protective relay interprets as a fault condition. GTG number 3 trips last, a 0.3 second delay. When the shock deformation of the generator mounting frame causes a micro misalignment in the rotor that the vibration sensor detects as an incipient bearing failure, the emergency diesel generator starts automatically as designed and provides 440 volts to the emergency bus, enough for emergency lighting, fire pumps, basic sound-powered communications, and the passive sonar system. It cannot power the Aegis combat system. It cannot power the SPY-1D radar. It cannot power the Mark 41 vertical launch system. It cannot power the main propulsion turbines. The Wilbur is stationary in the Philippine Sea, every primary system offline. At 2:10 a.m., the lights go out, not the emergency lights. Those are on the diesel circuit, and they glow their flat red from every compartment simultaneously as the main power drops. But the white light, the working light, the light that means the ship is running and operational and alive, that light goes out everywhere at once. And what replaces it is crimson shadow, and the sound of ventilation fans spinning down, dropping through their frequency range over 8 seconds until they stop. And then a silence that every sailor aboard recognizes as the most alarming sound a ship can make. Nothing. In Combat Information Center, 12 tactical displays go dark. The SPY-1D radar stops. When the power disappears, the radar disappears. The ship that was tracking contacts, managing its tactical picture, maintaining situational awareness in a hostile operating environment. That ship is now blind, stationary, and acoustically loud in a patch of ocean where the submarine that just engaged her is somewhere between 8 and 14 nautical miles away and is almost certainly already beginning the process of reloading. The submarine's commanding officer heard the detonation. He is running his passive sonar. He is listening for the sound of a ship under power. He is not hearing it. The general alarm sounds on emergency diesel power. 5 blasts, the most familiar sound in the U.S. Navy. The sound that every sailor is trained from their first day to respond to without hesitation. The sound that means leave whatever you are doing and go to your station now. The 1MC announcing circuit comes up on emergency power 30 seconds after the blackout. The commanding officer's voice is flat. All hands, damage control, engineering casualty. All department heads report to DC Central. Damage Control Central receives its first status reports at 2:11 a.m. The grease pencil is already moving across the laminated board. Red, GTG number 1, number 2, number 3. Offline simultaneously. Emergency diesel active, partial load only. Red. Main propulsion, offline. No shaft power. Ship stationary. Red. Aegis/SPY-1D, offline. No radar. No fire control. Amber. Forward berthing, frame 28. Personnel losses from shock impact. Number unknown. Amber. Fire main pressure, nominal but degraded. Diesel fire pump active. Black. Passive sonar. Active on emergency power. Submarine contact classification in progress. The chief engineer arrives at 2:12 a.m. He has been in the engine room since 2100, running a fuel system inspection. He was braced against a structural frame when the detonation hit. He has a cut on his right palm from the tool he was holding when it became a projectile. He is not thinking about the cut. He reads the board. All 3 GTGs offline simultaneously. A failure mode that his training has covered in doctrine, but that he has never seen executed in practice. Because in practice, the probability of all 3 generators tripping on the same event is low enough that it functions as a theoretical scenario. It is no longer theoretical. The cascade from this single failure state runs directly to total loss of fighting capability. No radar, no missiles, no propulsion, no maneuver. The ship cannot evade and cannot engage. In the Philippine Sea, with a hostile submarine in the area, stationary is a targeting solution. He has 26 DC personnel available across the 3 damage control repair parties. The task is focused in a way that flooding and fire scenarios are not. There is no competing priority demanding attention while the flooding spreads. There is one problem. It is the right problem, and it is the worst possible version of it. Restart all 3 GTGs in total blackout, in a ship moving in heavy swells, with a submarine repositioning for a second engagement. He assigns the full engineering watch to the GTG restart sequence. He takes GTG number 2 himself, the center generator, the one with the most complex fault condition. Because the voltage spike trip is a relay reset and a system inspection, and he wants to clear it personally before any restart attempt. He assigns the most senior machinist's mate to GTG number 1 and sends the second engineering watch section to GTG number 3. He made the decision in under 40 seconds. 14 years at sea, compressed to a single assessment. 3 generators, 3 spaces, 26 people. He knew what each one needed. He did not convene a discussion. In the forward sonar room, running on emergency diesel power, the passive sonar operator is working the problem that matters most to every person on the ship. He has lost the Type 039B's track in the post-detonation noise environment. The torpedo's detonation, the Wilbur zone shock response, the cavitation from the emergency rudder application, all of it has filled the acoustic environment with masking noise that is only now beginning to decay. He is listening to the ocean through the thin steel of the hull with headphones and a display that shows the frequency spectrum in green lines on a dark background, looking for the specific acoustic signature of a submarine at low speed. The blade rate of the propeller, the frequency line of the reduction gearing, the subtle hull resonance of a pressurized cylinder moving through water. The ocean gives him nothing for 90 seconds. Then, at 2:13:41 a.m., a faint intermittent line appears at the upper edge of his display. He classifies it. Bearing 022. Estimated range 12 to 15 nautical miles. Not stationary. Maneuvering. He picks up the sound-powered phone. DC Central sonar. Possible submarine contact. Bearing 022. Estimated range 12 to 15 miles. Contact is maneuvering. The chief engineer is already in the GTG number 2 space when the report reaches him via the phone relay. He has the electrical panel open and the fault log in his hand, reading the relay event data under a battle lantern held between his teeth. The fault is what he suspected. A voltage protection trip, not a mechanical failure. The relay needs to be reset and the bus needs a visual inspection before he attempts restart. The visual inspection requires light. He has the battle lantern. The battle lantern is sufficient. The bus inspection takes 4 minutes. The bus is clean. The chief engineer resets the relay manually, using the reset key on a chain around his neck. A chain he has worn every watch since his first deployment as a junior officer. Because the reset key is the kind of thing that disappears during emergencies and then cannot be found when it is needed. The key is always there. It is always on the chain. The GTG number 2 restart sequence requires the fuel system to be primed, the air start system charged, and a frequency check before connecting to the main bus. In normal operations, this takes 8 minutes minimum. In darkness, in a ship rolling at 2 degrees from the swells, with a machinist's mate holding a battle lantern at the panel while the chief engineer works the procedure from memory. Because the procedure card is laminated and is right where it is supposed to be, but it requires 2 hands to hold and 2 hands to work the panel. And a human body only has 2 hands. The sequence is compressed. The chief engineer runs the fuel prime from memory. 45 seconds. He confirms the prime by feel at the fuel inlet coupling. A wet fitting means fuel has reached the manifold. He charges the air start from the ship's compressed air system on emergency power. He checks the starting valve position by touch. A quarter-turn ball valve with a T-handle, and the position of the T relative to the pipe tells him whether it is open or closed without requiring sight. It is in the correct position. He hits the air start at 2:16:51 a.m. GTG number 2 does not start. The air start motor turns the turbine through 3 revolutions and stops. The chief engineer checks the air pressure gauge under the battle lantern. 85 pounds per square inch. The specification requires 90 pounds per square inch minimum for a reliable air start. 5 pounds per square inch below threshold. The shock event caused a partial release from the compressed air receiver. A fitting torqued to specification, but the shock load flexed it enough to allow a slow bleed from the valve seat. The ship's compressed air system has lost pressure in the 5 minutes since the detonation. He looks at the pressure gauge for 2 seconds. The ship carries 2 compressed air receivers. The forward receiver feeds the GTG air start systems on the forward bus. The aft receiver feeds the aft systems and carries its pressure independently. If the aft receiver is at full pressure, he can cross-connect the supply and use aft air pressure to start the forward generators. The cross-connect valve is in the machinery space passageway, midships, manually operated with a wheel handle. It has never been operated in service conditions. He picks up the sound-powered phone. DC Central, Engineering. I need the aft compressed air receiver cross-connect opened immediately. Midships passageway, frame 44, port side. Send whoever is closest. Now, in DC Central, the watch officer relays the order. A damage controlman from repair party 2 moves to the midships passageway. He finds frame 44 by counting the frame numbers stenciled on the overhead. The emergency lighting is dim enough in the passageway that he navigates by touch and count rather than sight. His battle lantern is in his left hand. His right hand finds the valve wheel at frame 44 and turns it counterclockwise. The valve is stiffer than expected. It has not been operated manually since the ship's initial sea trials. He puts both hands on the wheel, drops the battle lantern to the deck, and works the valve open in darkness using both hands and his full upper body. The valve opens after 8 seconds of effort. He does not know if 8 seconds is a long time or a short time. He knows the valve is open. The aft compressed air pressure, 112 pounds per square inch, full charge, undamaged by the shock event, feeds into the forward supply line. The chief engineer is watching the pressure gauge when it moves. 85, 88, 91, 93. He hits the air start again. GTG number 2 catches on the first revolution. The LM2500 turbine accelerates through its startup sequence. The sound rising through the machinery space from a mechanical whir to a sustained high-frequency howl in under 30 seconds. The frequency meter climbs. 45 hertz, 50 hertz, 55 hertz. The chief watches the output voltage stabilize. 440 volts, 60.2 hertz, within specification. He connects GTG number 2 to the forward main bus at 2:19:14 a.m. The lights in the forward section of the ship shift from red to white. They do not come on all at once. The switchboard's load distribution logic brings systems online in priority order, shedding non-critical loads to ensure the critical systems have stable power before the full load is accepted. The sequence takes 40 seconds. During those 40 seconds, emergency lighting remains active. DC Central status board becomes fully visible in white light for the first time since 2:10 a.m. The engineering status boards update, and the forward ventilation fans spin back up. The sound of them is, in this ship at this moment, the most welcome sound any person aboard has heard in 9 minutes and 14 seconds. In CIC, the Aegis combat system begins its initialization sequence. The SPY-1D requires 89 seconds of self-diagnostic before the phased array goes to active scan. The operations officer is already at his console. The tactical display is loading from the last saved state. The initialization bar advances. The sonar operator's sound-powered phone buzzes. His voice is controlled, but there is urgency underneath the control. DC Central Sonar. Contact update. Bearing 018. Range 9 miles. Decreasing. Contact has increased speed. I assess the Type 039B is conducting a repositioning run for a second engagement. Time to minimum firing range. Estimated 7 to 9 minutes. 7 to 9 minutes. GTGs number 1 and number 3 are not yet restarted. The machinists' mates in those spaces are working their own restart sequences. GTG number 1 has a stuck igniter that has to be manually cycled by reaching into the igniter housing with a probe tool while the turbine is on air start, requiring 2 people to work simultaneously in a space designed for 1. GTG number 3 is in better shape. Rotor alignment confirmed. Primary fault cleared. Needs only a clean compressed air charge and a restart attempt. GTG number 2 alone is running. The ship has partial power. Partial is not sufficient for what is coming. The chief engineer does not have time to supervise both spaces simultaneously. He takes the sound-powered phone and talks the GTG number 3 watch through the restart sequence step by step, one instruction at a time, his voice flat and precise. Fuel prime confirmed. Air start valve position confirmed. Igniter status confirmed. Air pressure, drawing from the cross-connected aft supply, confirmed at 108 pounds per square inch. Start. GTG number 3 starts on the first attempt at 2:21:03 a.m. The main propulsion system accepts power from the dual generator bus at 2:21:40 a.m. following a 37-second load acceptance test. The propulsion control console in the engine room shows the familiar green status indicators for both operational shafts. The chief engineer looks at those indicators the way a man looks at something he was not certain he would see again. He picks up the intercom. Bridge, engineering, main propulsion available. You have full shaft power. The commanding officer, who has been conning the ship by voice command from the bridge with no radar, no propulsion, and a submarine bearing down on him for 9 minutes, acknowledges the report without inflection and immediately orders a head flank and a course change to the northwest. The ship begins to accelerate. The hull, which has been sitting broadside to the swells during the entire blackout, begins to stabilize as the bow comes up into the wave direction, and forward motion provides directional stability. The SPY-1D initialization completes at 2:21:58 a.m. Active scan begins. All 4 phased array faces energize at 4 megawatts. The radar sweeps 360 degrees of ocean and airspace for the first time in 11 minutes and 48 seconds. And the data that comes back begins filling the tactical display in CIC with contacts. Surface traffic at distance, the Miyako Strait geometry to the northwest, and at bearing 016, range 7.2 nautical miles. A periscope depth contact. Classification submarine, moving at 8 knots. The operations officer calls the contact immediately. The commanding officer orders a course change to unmask the port torpedo tubes. 2 Mark 54 lightweight torpedoes, the ship's primary anti-submarine system, are ready in the Mark 32 tube launchers. The fire control solution is generated in 11 seconds from the SPY-1D acquisition data, processed through the integrated sonar fire control system using the passive track that has been building since 2:13 a.m. The solution quality is assessed at 88%. The Type 039B's commanding officer has been running his approach at increased speed. The speed that was his mistake, because higher speed increased his own acoustic signature and gave the Wilbur's passive sonar a better track. He was not aware that the Wilbur had regained power. He was expecting to find a stationary, powerless ship at the end of his approach run. His periscope scan at 2:22 a.m. shows him something different. a destroyer at speed, bow wave visible, on a course taking her beam on to his position. He can see the SPY-1D array faces active. He begins to order a deep dive. At 2:22:31 a.m., the Wilbur fires. Both Mk-54s, sequential, 11 seconds apart. The first torpedo is in the water. The Type 039B goes deep at maximum safe rate. It is a fast dive. It is not fast enough. The first Mark 54 follows the target's acoustic signature through the water column, its active seeker acquiring the 039B at 800 meters range. The torpedo runs to detonation in 42 seconds. At 2:23:13 a.m., at a depth of 180 meters and 9 nautical miles northeast of USS Curtis Wilbur, the Type 039B ceases to be a factor. The second torpedo is recalled via its wire guidance link. It circles once and sinks. In CIC, the operations officer marks the contact as neutralized. The tactical display shows clean ocean. The SPY-1D continues its sweep, looking for what might come next. The commanding officer orders a reduction to 18 knots and notifies the battle group commander via encrypted data link. The battle group commander requests a status report. The ship could fight. The ship could move. 11 minutes and 48 seconds of lost capability. Recovered by hand, in the dark, at sea. The true cost revealed itself in the hours that followed. GTG number 1 did not restart cleanly. The stuck igniter assembly was damaged during manual cycling, and the generator was returned to service only after the senior gas turbine systems technician rigged an improvised bypass using a fabricated tool and a section of conduit cut from a damaged bracket. The generator ran on that bypass for 290 nautical miles to Okinawa. It held. 7 crew members sustained injuries from the shock impact. Fractures, contusions, lacerations from objects driven airborne in the 0.8-second lateral acceleration. One sailor was found unconscious beneath a collapsed rack in forward berthing and was treated for a concussion 20 minutes later. He was fortunate. If the U-6 had detonated at 40 meters lateral offset instead of 60, structural analysis conducted after the fact places the keel stress above the design limit at 3 frames. There are no surviving margins on a failed keel in the Philippine Sea. The chief engineer ran the numbers on paper after. At 40 meters lateral offset versus 60, the keel stress factor increases by a coefficient of 2.3. The margin was not 14 inches of weld seam. It was 20 meters of open ocean. The ocean gave those 20 meters. The crew did not have the option of providing them. What the crew provided was 11 minutes and 48 seconds of engineering work in total darkness at sea. With a submarine repositioning 9 miles out, they provided a compressed air cross connect found by touch in a dark passageway. They provided a fuel prime sequence run from memory. They provided a valve opened with both hands and no light by a damage controlman who knew where frame 44 was because he had spent enough time in the midships passageway to know the ship by its bones. One U-6 torpedo detonated at 60-meter lateral range and 80-meter depth. 3 gas turbine generators offline simultaneously. 11 minutes and 48 seconds of full electrical blackout. Main propulsion offline for the same duration. SPY-1D radar and Aegis fire control offline. 2 Mark 54 torpedoes expended in terminal response. GTG number 1 restored on improvised bypass. 4 hours of field repair. 7 personnel sustained injuries from shock impact, 1 requiring medical observation. Compressed air system pressure depleted by shock-induced fitting failure. 1 improvised tool fabricated in the field, still in the DC locker on arrival in Okinawa. Ship status operational. The yard teams who assessed the Curtis Wilbur 2 weeks later found the improvised igniter bypass still in place on GTG number 1. The lead technician examined it before writing his report. The fix was not standard. It was not in any documentation. It was, by every engineering standard he applied, correct. The formal documentation was never written. The technician transferred to a new command before the paperwork could be completed. But the fix exists in the ship's maintenance log, in handwriting, waiting for the next time someone needs it. The procedure is written in offices. The ship is known in the engine room, in the dark, with a hostile submarine repositioning 9 miles away and the pressure gauge reading 5 psi below the threshold you need. That knowledge does not transfer by manual. It transfers by hand.